Hello and welcome back. In this video, we are going to see complexity of algorithms. Analysis of algorithms is a major task in computer science. In order to compare algorithms, we must have some criteria to measure the efficiency of our algorithms. So let's assume that we are having two algorithms and both the algorithms are solving the same problem. Then we may face a problem that which algorithm to choose, right? So here we will be selecting the algorithm that performs well based on some criteria. So let's assume that we are having M as an algorithm and N is the size of the input data that we have. So we are having two main measures for efficiency or complexity of algorithm, and these are time complexity and space complexity. So what we mean by time complexity? Time complexity is measured by counting the number of key operations, for example, comparisons in searching or sorting. Whereas space complexity is measured by counting the maximum of memory needed by the algorithm. So time complexity actually deals with the number of key operations those are performed, right? So if we are having the same algorithm that is running on two different processors, then it is possible that the time required to compute may be different because the speed of the processor is different, right? But the algorithm is same. So here, while finding the complexity of algorithm, we are not actually finding the time, but we are considering the number of key operations those are required to perform the task. Okay, so whichever is the algorithm requires less number of computations, obviously the time complexity of that particular algorithm is good. So complexity of algorithms is given as a mathematical function f of n. So this function gives the running time and or storage space requirement of algorithm m in terms of the size of input data n. Usually, whenever we talk about complexity of algorithms, we refer to time complexity, which is the running time of algorithm m. So we may have worst case complexity, average case complexity, or best case complexity. So what is worst case complexity? It is the maximum value of function f of n for any possible input. So obviously the complexity is given in terms of this mathematical function f of n. So to determine the complexity, we need to evaluate this function f of n with respect to the data that we have. So the maximum value of f of n for any possible input is called as worst case complexity, whereas the expected value of f of n is given as average case complexity. However, the minimum possible value of f of n is the best case complexity of the algorithm. So, the most important thing here is how to compute average case complexity of algorithm. As I stated, it is the expected value of f of n. So, this assumes that a certain probabilistic distribution for the input data. Say for example, we may assume that all possible permutations of an input data set are equally likely. So if this is the assumption, then if we are having the numbers say n1, n2 up to nk, then if they occur with respective probabilities, say P1, P2 up to Pk, then the expectation or average value E is given as the sum of product of these respective numbers. So N1 into P1 plus N2 into P2 so on up to Nk into Pk gives us the expectation or average value E. So Let's see now one algorithm and how to compute the complexity of the algorithm. So here is the algorithm that is meant for sequential search or linear search. So we are following all the norms to write the pseudocode. So this is the pseudocode for sequential search. So we are locating the target in an unordered list of elements. So the precondition is list that we are sending as a parameter contains data array to be searched. List must contain at least one element. Last is the index to last element in the list. Target contains data to be searched. LOC is the address where the found element's index location is to be stored. And after completing this algorithm, the post condition would be LOC contains matching index or last index if the element is not found. And the return parameter is found, that is true or false. So in this algorithm, this is a similar algorithm we have studied earlier also. So we are having one running variable here, set looker to 0. And most importantly, we are having this loop, right? So in this loop we are checking the condition that whether looker is less than last, that means whether we have reached to the end of the list, and whether target is not equal to the element under consideration with respect to the position looker. So if we have not reached till end and if we have not found the target element, we are going to increment this looker, right? So this loop is really very important as far as the computation of complexity is considered. So usually while computing the complexity, we consider how many times the loop gets executed, right? So further, after coming out from the loop, either we find the element or the element is not available in the list. So if there is no match, then LOC will contain the last position. If there is a match, then our target is same as list looker, right? So if target is equal to list looker, then we are setting the flag found to true. Otherwise, we are setting the flag found to false, right? And we are returning this found, right? So this is our algorithm. Now we want to compute the complexity of the algorithm. So this is the algorithm that just we have seen. So we are computing the complexity in terms of worst case, average case and best case. So what would be the worst case complexity for linear search or sequential search? Obviously, the number of comparisons. So here, how many times this loop gets executed, we are going to look for that, okay? So if the element is located at the last position, or if there is no element found, then obviously we are going to execute this loop n number of times if we are having n elements in the list, right? So if I am having 10 elements in the list, and if the element that I am looking for is located at the last position, or if there is no element available in the list, then in both the situations this loop gets executed n number of times, right? So worst case complexity of linear search would be f of n equal to n, right? Now how to find average case complexity of linear search? Now here we are saying that the probability that the search element or the target element is available at location 1 is available at location 2, 3 up to n is equally likely, right? So probability that the element is found at position 1 is 1 divided by n. Probability that the element is found at location 2 is also 1 divided by n, and so on. So with this computation, as we have seen earlier, if we compute this particular expression, then what we are getting is n plus 1 divided by 2. So the average case complexity or the number of operations in average case complexity required are n plus 1 divided by 2. What about best case complexity of linear search? Best case occurs when the very first element in the list is the target element. So only one comparison is required, right? Or only once this loop gets executed. So best case complexity of linear search is f of n equal to 1. So one way to denote the complexity of algorithm is using Bigon notation. Though there are several such notations available in algorithm theory, we are going to look at only Bigon notation here in this course, right? So suppose M is an algorithm and N is the size of input data, right? Then complexity f of n of algorithm increases with the number of elements n. So if n increases, then complexity f of n also increases, right? Now it is important to examine the rate of increase of f of n, right? So if we would like to examine the rate of increase of f of n, then obviously we should look for some mathematical function, right, to which we can compare this rate of increase of f of n, right? So we are going to compare the rate of increase of f of n with some standard function g of n, and this standard function g of n may be log of n to the base 2 or n log n square, n cube, 2n and so on, right? So we are going to make use of functional O notation, which is also known as big O notation, right? And it is denoted like f of n is order of g of n. We are comparing rate of increase of f of n with the some standard function g of n. So it is important to note these points. If algorithm does not contain any loop or recursions, then its efficiency is a function of the number of instructions it contains. However, if the algorithm is having the loop or algorithm is having recursion, then the efficiency of both of these algorithms vary widely. So, as I stated earlier, the complexity of the algorithm usually is being computed based upon the loops and how many times the loop gets executed, right? So depending upon that, the complexity is determined. So let's consider the linear loop, right? So here we are having a for loop and I is the running variable that varies from 0 to 1000, and every time I gets incremented by 1. So whatever may be the application code that is being executed those many times in the loop, right? So let's try to answer now this question. How many times the body of the loop is repeated? How many times the body of the loop is repeated? So obviously the answer would be 1000, right? So here number n is 1000, right? So number of times this loop gets executed is 1000, right? So here n is 1000. So obviously the efficiency is directly proportional to the number of iterations. Okay, and this is how we say that the complexity of this algorithm is given as f of n equal to order of n, right? So this is meant for linear loops like this. Now let's talk about the logarithmic loops, right? So we are having here a for loop wherein I varies from 1 to 1000, but every time I gets incremented by twice, right? So I is equal to 2 into I. Okay. the similar kind of loop we have here. So in this for loop, for every loop I gets decremented as I equal to I by 2, right? So every time the value of I would be half of that, and here every time the value of I would be twice of I. Okay, so those many times, in both the cases, those many times the application code runs. So let's see now how many times the body of the loop gets repeated, right, in both the cases. Here I gets incremented as twice of the old I, and here I is being divided by 2, right? So how many times the body of this loop is repeated? So the answer to this question is 10 times, right? So here n is 1000, okay, and the execution of this code would be for 10 times, right? So what would be the relation now between this n and the number of times the code gets executed? So this is given as f of n equal to order of log of n to the base 2. So for logarithmic loops like this, the complexity of the algorithm with Bigon notation is given as order of log of n to the base 2. Now another construct that we may have always in our programs is the nested loops. So if in our algorithm we are having the nested loops, then the number of iterations are computed as the multiplication of the outer loop iterations and inner loop iterations, right? So how many times outer loop executes, right? So those many times entire inner loop gets executed. So multiplication of both these iterations would be the number of iterations required in case of nested loops. So we may have several kinds of nested loops. We may have linear logarithmic loops, we may have quadratic loops, or we may have dependent quadratic loops, right? So let's see the complexity in case of all these different kinds of nested loops. Now see here, this is the example of linear logarithmic loop, right? So we are having nested for loops, okay? The outer loop is linear, okay, and the inner loop is logarithmic because j is incremented as j into equal to 2. So every time j is twice of its old value, right? So the outer loop is linear whereas inner loop is logarithmic. Okay, so how many times now the body of this loop is repeated? So obviously the outer loop is linear, so here n is 10, so outer loop is repeated for 10 times and inner loop is repeated for log of 10 times. Okay, so answer, how many times the body of this loop gets repeated? 10 log 10 times. Obviously this is log of 10 to the base 2. So the complexity of this algorithm can be given as f of n equal to order of n log of n to the base 2. Now let's look at the quadratic loop. So here we are having nested loops and both the loops are running for 10 times, right? So if n is 10 here, okay, then how many times the body of the loop is being repeated? Okay, so here the answer obviously is 100 times. So the number of iterations for outer loop multiplied by number of iterations in the inner loop. Okay, so obviously the answer would be 100 times. So for quadratic loops, the complexity is given as order of n square. Now let's talk about dependent quadratic loops. So see here, the outer loop is linear, right? N is 10 and the inner loop depends upon the outer loop. So j varies from 0 to less than I, where I is the running variable for the outer loop. So such kind of construct is actually known as dependent loop, right? So if we are having such kind of dependent loops, then how many times this gets executed? So the number of times the code gets executed is n into n plus 1 divided by 2, right? N into n plus 1 divided by 2. Now in general we need to compare this number of operations with some standard form. So if we consider this n into n plus 1 by 2, then obviously this becomes n square plus n divided by 2. Okay, so if it is n square plus n divided by 2, then the maximum power in this polynomial is 2, right? So order of n square would be the efficiency or complexity for dependent quadratic loops. So now let's try to summarize different types of loops and the respective complexities of the algorithms. So the assumption is we are using a computer that executes 1,000,000 instructions per second and the loop contains 10 instructions. Each iteration of the loop requires 0.00001 second and the number of elements those we have n equal to 10,000. So we are having now the efficiency Bigon notation for the respective kind of loop that we are having or the work that we are performing, then the number of iterations required and the estimated time with respect to this particular configuration. So if the loop is logarithmic, then the Bigon notation would be order of log of n to the base 2. The number of iterations required are 14. We are considering n equal to 10,000 and the estimated time would be in microseconds. If we are having linear loops, then the efficiency would be order of n, number of iterations obviously 10,000, then the estimated time would be in seconds. If it is linear logarithmic loop, then Bigon notation would be order of n into log of n to the base 2. Number of iterations required are 1,40,000 and the estimated time would be in seconds. If it is a quadratic loop, then order of n square would be the efficiency. 10,000 square number of iterations would be required and the estimated time would be in minutes. If it is a polynomial time or the polynomial operation, then we require the efficiency of the algorithm would be order of n to the power k, then the iterations 10,000 to the power k and the estimated time would be in hours. If it is exponential, then order of c to the power n, then the number of iterations would be 2 to the power 10,000, so 2 raised to n, okay, and the estimated time would be intractable. Whereas if we are computing the efficiency of this operation of factorial, then the Bigon notation would be order of n factorial. So number of iterations required are 10,000 factorial and once again the estimated time would be intractable. So with this we are concluding this video on complexity of algorithms. So thank you and wishing you the very best for learning. Please like and share this video, and if you have not subscribed the channel, do subscribe the channel.